So we're lecturing for those?
All right, so today, yes, we are going to calculate. So get out your calculators, get out your equation sheets. We are going to learn about titrations.
Our favorite.
We did 1 day of titration in this class. All right, good. We are going to do more than 1 day in this class. So, what is a titration?
It's a balancing of process of titration.
Dang, you got it. We're supposed to snack you today, Louis. Yeah.
I
I think it has something to do with like the amount of like acids or base need to neutralize the other.
Okay. Doesn't have to be an acid base. We can actually do redox titrations as well. But the point is, we add something that we want to know the concentration of. We take something that we do know the concentration of, and we mix them together. By carefully measuring how much of the known concentration thing it takes to react with the unknown concentration thing, we can do some stoichiometry and figure out how much of the unknown is in there. Okay? So the setup that I'm going to do is, I've got in this graduated cylinder here 48.5 milliliters of an unknown concentration of HCl. I'm going to put that into this fancy little piece of glassware, which is called Erlenmeyer flask. Why does it have that weird shape?
So you could mix it.
Erlenmeyer was so that you can swirl it around and not have to worry about things splashing out, especially if they're acids or bases. You don't want to splash them out of there. In fact, I'm going to add, well, first I'm going to add a magnetic stir bar. So that I don't have to do any work, I can just crank it up and this thing will stir itself. Now even if I go crazy and crank it to 10, still the shape of the Erlenmeyer flask is going to prevent any from spilling out and getting all over the place, okay? Now I have to add something else to do an acid-base titration.
Indicator.
An indicator. What's an indicator? Something that indicates. One who indicates, yes.
Changes color.
An acid-base indicator is a substance that can change its color under different levels of acidity and basicity. Okay? But here's the thing to keep in mind. All acid-base indicators are actually weak acids. So when I add this indicator to my flask, do I want to add like 30 milliliters so it's nice and dark green? No, we want to add as little as possible and still be able to tell the color, because if I add too much of this, this is actually an acid. It will react with the base that I'm going to be adding out of here. Okay, so if I add too much, it's going to affect my results. Usually just a few drops. Can you tell what color that is?
Pink.
It's pink. Okay, if you can see the color, that's all you need. Now, just for the YouTube viewers, for Nicholas, who's like way back there, I'm going to add more than you would normally add for a titration. Okay, nice and dark pink. Now, when I said that I need to add an indicator, that's not exactly true. I just need something that's going to allow me to keep track of the pH. So I could actually add a pH probe. We're going to do that in the lab this week. Okay, but I can't add a pH probe right now. Why not?
You don't have one.
I don't have one. Why else? The level of liquid in here is actually not deep enough for me to get a pH probe in far enough to get a reading. Okay, so what you can do with titrations, once I've added my unknown and I know exactly how much I've added, I can add water. Because all I'm really trying to do in this titration is to figure out at what point have I added the exact number of moles of substance up here, the titrant, to the exact number of moles of stuff that I put down here, the analyte. Okay? So I've got HCl. What I'm going to titrate that with is 0.1 molar NaOH. And we're going to assume that whoever made this made it very carefully, and so it is 0.100 molar NaOH. Now, how am I going to get it in there? Put it way up above my head and get up in there and no! You would not believe how many times I see people, and it's always like the shortest person.
That was us last year.
Take it out for crumb's sake.
And turn it upside down.
Exactly.
Get a funnel.
Wow. Nice one.
That's clean enough. This is just for demonstration purposes. Okay, and so now I'm going to keep it below my face level. Who cares?
It's above face level.
Okay, it doesn't really matter where I start. Now ideally I want to start reasonably close to 0. If I start at 49, I don't have a whole lot of measurements that I can make here, okay? But I do not have to start exactly at 0. That's a waste of time. And in fact, if I run out, I could record the amount that I've added. I could always add more in there and keep going. All right? But right now, this is another thing. People try to read the volume. Oh, it's 10.5. No, you're just really far below the meniscus. I got to get myself up there or lower the burette. That's actually probably better. So I'm not, whoa. So I'm not trying to like be on my tiptoes and like cause an accident. Okay, lower the burette. Let's see where we're at. Ooh, eye level, perfect. Now, numbers count down, so I gotta realize 9 is here, 10 is here. I'm between 9 and 10. I'm at 9.71. That's my starting volume, 9.71 milliliters. That's important because everything I add, when I read my final volumes, I actually started at 7. What did I say? 9.71. Did I say what this thing is called? A burette. And I put 0.100 molar NaOH. Okay. Now, what reaction is going to occur? I took HCl and I reacted with NaOH. What happens?
H2O.
I produce H2O and NaCl. Now, this is the full molecular equation. But we know HCl does not exist dissolved in solution. It's a strong acid, right? Yes. So what's really in there? Cl minus and H plus. Bronsted model, H3O plus.
Oh, yeah.
H3O.
H plus does not exist floating all by itself. Hey, I'm an H plus, look at me. No, it's always going to be attached to somebody. When in doubt, it's attached to water. So H3O plus is actually reacting with what? OH minus. NaOH is soluble. All sodium salts are soluble, so NaOH doesn't exist in solution. It's Na plus and OH minus. The Na plus doesn't do anything. It's the OH minus that undergoes the reaction. What is the product? H2O plus another H2O. Okay? And I think in your outline it actually says, under 6C1, part I. That's weird. For a mixture of a strong acid and a strong base, the neutralization reaction is H2O plus OH minus yields H2O. That's not right.
Where?
Two H2Os.
Where is it?
This is under I and then subpart I. Knowledge nugget I, sub bullet
What page is it?
1, sure, whatever. Okay? We have to understand what reaction occurs for different types of titrations. For a strong acid, strong base, this is what's going to happen. Now this reaction looks very familiar to me. Sort of. Sort of. She said it's like the equilibrium for regular water. What do you mean by that?
Like,
We saw this.
Split.
We saw this reaction flipped in the simulation, right? If what simulation?
No, you didn't.
The one that we just did, the acid-base simulation. When water molecules collide, if I have pure water, there's actually a chance that two water molecules can collide and spontaneously produce H3O plus and OH minus. That's called the autoionization of water, the reverse of this reaction. That was one of the reactions we saw in that simulation. What is the K value for the autoionization of water?
1.0 times 10 to the negative 14.
1.0 times 10 to the negative 14th, right? That's on your equation sheet. If you don't know where it is, get out your equation sheet and look for it. It says Kw, it even says it's concentration of H3O plus times OH minus. That's because those are the products of the reverse reaction, right? And it says it's equal to 1.0 times 10 to the minus 14th. So if the reverse of this has a K of 1.0 times 10 to the minus 14th, what's the K for this reaction? 1.0 times 10 to the positive 14th. What does that mean? Is that a big K or a small K? Really, really big, which means very product favored. Okay? We can assume that this reaction goes to completion. That's why I only drew one arrow on it. Okay? So what we're going to do is we're going to treat this just like normal stoichiometry that we've done in the past. Okay? So, I'm going to show you first how to actually do the titration and figure out the concentration of the unknown. Then we're going to go back and use this equation to predict what the pH is at various points during the titration. Okay? So, what I'm going to do is turn this little knob here and let some NaOH come out and into my flask. Boring. Didn't look like anything happened. Now, if I turn the stirring off and I do it again, you can see that part of the flask is kind of turning purple. That should tell you that the stirring is important. Right? We want this to thoroughly mix so that we get a uniform color so we can actually get an idea of what the pH really is. Now this is an interesting indicator that undergoes a bunch of different color changes. So I've got a little scale here, and pink corresponds to light red, yes. Osmo, what's the pH if it's pink? 4. It's actually probably lower than 4. Anything below 4 will be pink with this indicator. Okay, so I'm going to add some more. Whoop! Did you see that quick change?
Yeah.
Okay, you have to be very careful when you're doing titrations. There will be a point where it's like nothing's happening, nothing's happening, nothing's happening. You check your Snapchat and boom, it's already passed and you're done and you got to start over. Okay? You have to watch this carefully. Now, if I had actually gone over, what I would do is I would start again and I would say, okay, well now I'm at about 24. I started at almost 10, so it took about 14 to react, right? So I would set it up again. I would get to like 11 and I would slow down this time, okay? Luckily I didn't go over, so I don't have to start over. I could see then from the color now, we're kind of that nice orange color, so we're at pH of 5. So when we're going to construct our titration curve, we started out at 4, when it was kind of pink. And now my volume is 24.08.
His volume
At 24.08, yes, volume added. I'll say volume 0.100 molar NaOH added. At 24.08, now we are orange. All right, it was pink, 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 pink. Now we're orange. Now I'm going to go real slow, like drop by drop slow, because I do not want to go over. Woo!
Oh my god.
That was 2 drops I thought I went over, right? Did you see how it was green?
Yeah.
And now it's settled into sort of a
Yellow.
yellowish color, which means we're up to pH 6. And now I'm at 24.2. So I went up a whole pH point with just a drop, 2 drops. Okay, so I am very, very close here. There's a drop hanging. Okay, still yellow, we're okay. Okay, I'm gonna crank my string up because this is kind of cool to watch. Ooh.
That one drop though.
Whoop!
Green.
It was really almost like a blue-green. What is it now?
I know. Wait, let that jump off. Oh, wait,
Okay,
that's
so pH 7 here is pretty close. I would say we're close. So what I'm going to do is I'm going to record the number. We are at 24.50. Now if I had a drop and it turns blue and I went past, well, at least I have the measurement now that I can compare to, right? Well, let's see.
Get that one drop.
That one drop. Just
No, just tap it.
whoop. All right. Do you think we nailed that green, or do you think we went over?
Yes.
I think it's pretty good. All right. So our final volume reading was 24.52.
Let's see if it turns blue.
I know.
You just add a lot to see what happens.
What if you turn? What if you dump the entire?
Hey, Mr. Bull.
Okay. So now we are green, which is pH 7, 4, 5, 6, 7. And we're still only 20, what did I say, 24.52? Okay, so we're still not even to 25 here. So we got a really, really sharp increase in the pH.
Well, what's it when it was 24.08?
Yellow, really. Well, no, 24.08 was the first one. That was pH 5. Then I added a few drops. I don't think I told you the value.
It was
But
24.2.
24.2, it went up to 6. Then 24.52, now we're done. We're at 7. Okay. Now, if I keep going here, let's just add some more drops.
Yeah.
Now, the next thing here is sort of this blue-green color. That's pH 8. Let's see if we can get that one.
It's blue.
I think it's sort of that nice aquamarine color. Nice. And we are at 24.70.
Is that 8?
What?
Is that pH 8?
Yep, pH 8. So again, we're adding just tiny amounts. We're still not even getting to 25. Okay. Now I'll add some more. I want to try to get that nice dark blue color.
Running out of room on my graph.
That looks pretty good there. It's diluted, but it's pretty much the same color. Now we're over 25, 25.30.
That's page 9.
Yeah, pH 9. Okay, now it should turn purple when I get to pH 10. Purple? Lavender. Now that's actually at 26.0. So we're starting to kind of have to add more to get that same increase in the pH. I don't have a purple marker here, but okay. What's pretty much happening is this.
I've lost count of what pH is.
I have the
We're going to start to level off. Huh?
I've lost count of what pH we're at.
We are, purple is pH 10 or higher. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So that's the general shape of the curve. But what was the point of doing this titration?
To show us how to titrate.
We wanted to see pretty colors. No, we wanted to know what is the concentration of this HCl.
Stoic, so you find the
Now we got to do stoichiometry. Okay? Well, we know the volume of HCl, but we don't know the number of moles, so we can't find the concentration. But we can get the number of moles of HCl because we know when we got to pH 7, we had equal amounts of H3O plus and OH minus. This point here at pH 7, the point with the sharpest change in pH, this is called the equivalence point. Called the equivalence point because you've added equivalent numbers of moles of your acid and the moles of your base. For a strong acid, strong base titration, your equivalence point should occur at a pH of 7. Because once we add equal moles of both of these, they will completely react with each other and we'll be left with water. What's the pH of water?
7.
7, right? Because of that autoionization. Okay? So, let's see. How much NaOH did we actually add? Well, we started at 9.71, we ended at 24.52. What was our total volume added? Question on that? Just subtracting where I ended from where I started. So we added 14.81 milliliters. It was 0.1 molar. So if I use the molarity equation, 0.100 molar, we added 0.01481 liters. How many moles of NaOH do we add? 0.001481 moles. Agreed?
Yeah.
Okay. Now, if we know that we are at the equivalence point, we've added equivalent number of moles. Well, if we added 0.001481 moles of NaOH, how much HCl was in there? The same amount. Because for this acid and this base, we have a 1-to-1 stoichiometric ratio, that means that we had 0.001481 moles of HCl. Agreed?
Yeah.
Now, because I recorded the volume initially, we can use the molarity equation to figure out the concentration. 0.001481 moles of HCl in 0.0485 liters is what?
0.0305.
Cool? All right. That is the main purpose of a titration, to figure out what is the concentration of an unknown substance. We do that by adding a known concentration of substance, recording the volume that it takes to completely neutralize the unknown, and then we do a little stoichiometry. All right? Now, something else you might be asked to do on like a quiz or a test or like AP exam coming up in
Let's not talk about it.
how many weeks from today? I'm talking about the actual AP exam, not your final. 3 weeks? Woo! All right. You might be asked to calculate the pH at various points during this titration. How the heck do we do that? Well, let's do a calculation. Let's figure out what the pH was at 5 milliliters. Let's do it at 15 milliliters. And let's do it at 30 milliliters. Well, 5 milliliters. Let's see, what have we done? Well, if we have added 5 milliliters of NaOH, and we've mixed it with 49.2 milliliters, sorry, 48.5, 48.5 milliliters of 0.0305 molar HCl. What is the pH? Okay, now for these types of problems, they're going to tell you both concentrations because they want to know that you can do the calculation to figure out what that pH is going to be. Well, how do we do it? It's a limiting reactant problem. Let's figure out how many moles of NaOH we've put in there, how many moles of HCl we've put in there. Well, if we use the molarity equation, it was 0.100 molar. We've added 0.005 liters. So how many moles is that? Moles of NaOH. The HCl it was 0.0305 molar, and we had 0.0485 liters. That I can't do anymore. Point what? Agreed?
Yeah.
Sure. Who's our limiting reactant? NaOH. What do we know about the limiting reactant?
That's the product you can make.
That's the amount of product we can make. It's also the one that's going to be completely used up, right? So at that point when we added 5 milliliters, you saw the color didn't really change because all that OH minus that we put in there got gobbled up by the H3O plus. Okay, and we still had quite a bit of excess H3O plus in there. So what we have to do now is figure out how much excess HCl was in there. Well, if we started with 0.00148 moles of HCl, we know because of the stoichiometry, we used this number of moles of NaOH, so that's how many moles of HCl should have reacted, right? So I can actually subtract that. If I want to show it for completeness, I can do stoichiometry and convert this to moles of HCl, right? So this is how much we had to start. This is how much we used when we added our NaOH. So how much remains? Wait. I missed a 0 here. Whew. I got scared. I'm like, wait a minute. 0.001 minus 0.005. So 0.00098 moles of HCl. HCl in excess. Now, what was I actually trying to find? pH. So this is where it gets a little tricky. Now we have to take that number of moles, and what is our total volume right now?
Add those two.
Yeah, we got to add 48.5 and 5. That's 53.5, so that's our new volume. So what's our molarity? Everybody agree? Okay. 0.00098 over 0.053.
Oh, I put 5.
So I put 0.053, so that's 0.
Oh, it is 535. Well, if that was 5.0, yeah, same thing problems, whatever. So now we're 0.0183?
Yeah.
Now again, this is a strong acid, so I've been using HCl, but really it's H3O+, right? So if we know the concentration of H3O+, let's take the negative log of that and let's see what the pH is.
1.7 or 1.76.
Okay, so it turns out here, my graph was a little weird because the indicator only tells us it's below 4 is pink. The real pH was 1.7, right? What's the pH of the original solution? Before I added anything. Well, we found it was 0.0305. What's the pH of this? What is it? 1.5. So we actually started at 1.5. Now we're at 1.7. Okay? So a little bit lower than what we could see with the color. Okay, so a pH probe would have been good for that. Now, actually, let me talk about indicators for a minute, because the indicator that I added was a really weird indicator. Does anybody have any questions about this? The indicator I added was a strange one. It's actually a mixture of 3 different indicators. That's the only way I could have got all those pretty colors for you. Most indicators only have 2 colors. One when they're in acid, and one when they're in a base. Well, that's all we really need them to have, because all we really want them to do is change color when we've added equal number of moles. Okay? Now, here's a pretty complete chart of indicators. On the top, we've got pH. We've got the names of all these nasty things here. Methyl violet, crystal violet, ethyl violet, brilliant green, malachite green. And then over here, we've got some colors. Now this, I think this chart is a little bit confusing because it makes it seem like this thing is yellow 0, by about 1.6 it turns blue, and then what happens here? It's not very clear. This one doesn't have as many indicators, but it makes it a little bit clearer. There's a certain pH at which these indicators change their color. Anything below that pH, they're going to stay one color. Anything above it, they're going to stay the other color. Okay? So whatever these ones were in this other chart, methyl violet, the first one, anything above 1.6, it's blue. It's going to stay blue. Okay? So it turns out that different indicators all change their colors at different pH values. So we're going to have to choose the right indicator for the titration we're trying to do. For a strong acid, strong base titration, what's the pH at the equivalence point? 7, Hope, absolutely correct. So we want an indicator that changes its color right around 7. Lachmoid, yeah. Sounds like a bad guy in a Power Rangers movie. Who's Lachmoid?
That's not gonna be.
You don't like that one?
It's on the web.
Bromothymol would work pretty well too, right?
Yeah.
What's going to happen with bromothymol when I do this same titration? It's going to be yellow, 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 yellow. Bam! It's going to go blue.
What about green?
Green, you might see the green. If you are lucky and you've added just that right drop, you might see the green. Okay? But probably what's going to happen is it's going to be yellow with maybe a slightly greenish tint, and then you're going to add 1 or 2 drops, and then it's going to be blue with a slight green tint. That's okay though. 1 drop does not have a huge amount of volume. Okay? But because the pH changes so rapidly at the equivalence point, you're probably not going to see this green at all. It's probably going to go right from yellow to blue. Okay? But bromothymol blue, this bromothymol here, would be a good indicator to use for a strong acid, strong base, because we know the equivalence point is going to be at a pH of 7. Okay? We'll come back to this chart in a second. I don't think I need to do 15 milliliters, do I?
No.
It's going to be the same sort of work right here, okay? But again, if I kind of draw this thing, that's what it really should have looked like. Maybe even steeper here, okay? But what about 30 milliliters? What if we're past the equivalence point? Then how do these calculations change?
Not by much.
If we go past the equivalence point, HCl is the limiting reactant. So what?
You have to like to.
You have a question? I did.
Are you answering?
I don't even remember the question anymore because I just lost my train of
What
thought.
do you do? Like you, HCl.
What if HCl is a limiting reactant? What if we added more NaOH than we had HCl in there?
Oh, there's then we gotta see how much excess and.
All right, so let's do it. All I got to do is make some small little changes here. So now we've added 0.003 moles of NaOH. We only had 0.0014 moles of HCl. So now we're going to say, well, 0.003 moles of NaOH at the start minus 0.00148 moles of NaOH used, right? Because that's how much it'll take to completely use up my HCl. How much is left over then? 0.00152. Now what's the total volume at this point?
78.
75 liters is what?
0.019.
What's the negative log of this? What'd you get? 1.7.
2.8.
Negative log of 0.0194. What? 1.7. Ah, yes, we have to be very careful. We're talking about NaOH, so we take the negative log of this, that's actually the POH is 1.7. So 14 minus that is 12.3. Okay, so up here, our pH is 12.3. That's the only difference. When you pass the equivalence point, you just use the amount of excess thing that's been added. The only thing that makes these challenging is knowing whether you have excess acid, whether you have excess base, and knowing how to find the pH from that. Okay? All right, take a quick break, get something to drink, wake yourself up, and then we'll do a weak acid titration.
Oh.